Hi, Wildcats. You at this point have looked through the notes and the text and the videos, and you have an idea of Newton's second law. So I wanted to give you some example problems before you dove into doing some for yourself. So let's get started. Rob and Laura are studying across from each other at a 2-meter long table. Laura slides a resting book to Robert. If Laura applies a 1.6 Newton force to the 2.2 kilogram book, what is its acceleration? And looks like they also want to know how long it takes, so the amount of time for the book to get across the table to Rob. So as always, we write down what we know. We know the book has a mass of 2.2 kilograms. We know that Laura applies a force of 1.6 newtons. We are looking for its acceleration and how long it takes to get there. And it looks like they tell us the displacement of the book when it gets to the other end of the table will be 2 meters. It doesn't say anything about friction, so it looks like we can ignore that for this problem, so that's nice. So then the free body diagram of this is going to be there's some force of gravity, there's its normal force, and then there is an applied force here. And we're going to say that those two are the same. So there's our free body diagram. For acceleration, so we know from Newton's second law that acceleration is equal to the net force divided by the mass. In this case, the net force is just the applied force because normal force and the force of gravity would be equal but opposite. So we can disregard those and focus only on the force applied. In this case, we can say force applied is equal to F net. So from there, that just means F net is going to be 1.6 newtons, and the mass of the book is 2.2 kilograms. Now it's important to remember that we know a newton is equal to kilograms times meters per second squared. So when we think about that, the kilograms will cancel, and the only unit I'll have left is meters per second squared, which is good because we're solving for acceleration. So then acceleration is just going to be 1.6 divided by 2.2, which my calculator tells me is 0.727 meters per second squared. So that's the rate at which the book's velocity changes. Something that we missed before is the initial velocity of the book is 0 meters per second because it says the book is resting. So we can assume it has no velocity to start. So if we have acceleration, time, displacement, it's everyone's favorite topic, kinematics, will allow us to figure out how long or the time it takes. So if you look at your equation sheet, we know one of the kinematics equations is the displacement of an object is equal to its initial velocity times time plus 1/2 at squared. So since initial velocity is 0, that goes away. So displacement is equal to 1/2 at squared. We're looking for time. So we'll do some algebra here. The 2 gets rid of the 1/2. Divide both sides by acceleration. And then time is squared, so I got to take the square root of both sides. So I can say that time is equal to the square root of 2 times displacement divided by acceleration. So the square root of 2 times the displacement of the book, we know the table is 2 meters long. And we just figured out that the acceleration of the book is 0.727 meters per second squared. 0.727 meters per second squared. So the time will be 4 divided by 0.727, and then I'm going to square root that. which gives me 2.35 seconds. So it looks like it's going to take 2.35 seconds to get across the table. Okay, so easy problem done. Let's move on to something a little more involved. Here it says a horse pulls an 8 kilogram cart. So mass is 8 kilograms with a force of, so that's an applied force of 40 newtons at an angle, dang it, at an angle of 37 degrees. So we're going to have to do angles to some degree above the horizontal. The coefficient of friction, it's moving, so that's kinetic, between the cart and the ground is 0.35. If the cart starts at rest, so V initial is 0 meters per second, how far will it have moved after 5 seconds? So time equals 5 seconds. So if we went and looked at our kinematics equations, we would see that we're going to need its acceleration to solve for displacement. We're actually going to use that same equation that we just did in our last problem. So we're going to need acceleration. And we know acceleration is equal to force net divided by mass. So we have mass, but we need F net. And so this is an example of where the force applied, because it's at an angle, isn't F net. We're going to have to resolve all the vectors, force vectors, to determine the net force. So that means we'll need a free body diagram. So the cart has some weight and it has a normal force, therefore, and the force applied is 40 newtons at 37 degrees above the horizontal. So if here's horizontal, here is my force applied, and this is 37 degrees. And since they tell us the coefficient of friction, we're going to have to assume that friction is also acting opposite the cart's motion. So those are all the forces in play. We need to figure out what is net force. So this goes back to the types of problems that we did in focus question 1, where we saw how to resolve for those. If you need a review of this, you can go back. All the focus question 1 for unit 8 resources are still available, or you can email me, contact me, and we can go over that again. So let's get started. So this applied force I need to resolve for its horizontal, so force applied X, and its vertical component, so force applied Y. Let's see. We are gonna know, we're gonna assume that the acceleration is constant. So force applied X will be equal to the coefficient of, or the kinetic friction. Actually, no, that won't be true because this object is accelerating. So, and it's at rest. So let's start by determining what's going on up and down. We know that all the cart is only moving horizontally. It's not up and down. It's not coming off the ground. It's not going into the ground. So all the up and all the down forces have to be equal to each other. So what does that tell us? That tells us that force normal plus force applied Y will be equal to the opposite of the force of gravity. So normal force is not going to be just equal to the weight. So now I can start to think through, what do I solve for normal force? To solve for normal force, I can rearrange this. So force normal, run off the page, will be equal to opposite of force of gravity minus force applied Y. So force applied Y, I'm going to use some trigonometry to find that. So let's go up here and give us some room. So force normal is equal to the opposite. So force of gravity is just mass times acceleration due to gravity. So 8 kilograms times negative 9.81 meters per second squared. That's its weight, minus force applied y. So looking at this triangle, here's our angle. Force applied y is opposite of the angle, so I'm going to use sine. So force applied is 40 newtons, so it's going to be the hypotenuse, 40 newtons, times sine of 37 degrees. And that's all stays together. So there is how I solve for normal force. 8 times negative 9.81 is opposite of negative 78.48 newtons minus sine of 37 degrees. This is where you check to make sure your calculator's in degrees, not radians, times 40 means this is 24.07 newtons. So negative times a negative, this is a positive, 78.48. 78.48 minus 24.07 means the normal force is equal to 54.41 newtons. So now that I have normal force, I know the force of friction is equal to the coefficient of kinetic friction times the normal force. We covered that in focus question 1. So I can do 0.35, which they tell me is the coefficient of friction, times 54.41 newtons. So the force of kinetic friction is 19.04 newtons. And since I drew my picture to the left, this is going to be negative 19.04 newtons. All right. Now I need to get net force. F applied X is going to be trigonometry again. It's adjacent to the angle, so that will be cosine. So it's going to be the hypotenuse, 40 newtons, times the cosine of 37 degrees. So F applied X is cosine of 37 degrees times 40, which gives me 31.95 newtons. And that's to the right, so it's the positive direction. So when the cart is pulled by the horse at this angle, we know it's accelerating to the right. So net force must be to the right. So the net force in this case is going to be the sum of all the horizontal components, which is F applied X and force of friction. So it would be, I guess I'll write that out, force applied in the X direction plus force of kinetic friction. So 31.95 newtons plus negative 19.04 newtons minus 19.04. That tells me the net force on this is 12.91 newtons. Okay, that's good. So now I have net force and I have mass, so I can go back to Newton's second. Acceleration is equal to F net, 12.91 newtons, divided by the mass, which is 8 kilograms. So the cart will accelerate at 1.61 meters per second squared. Okay, so that's good, but now it wants to know if the cart starts at rest, how far has it moved after 5 seconds? So I need kinematics again. That's going to be delta x is equal to v initial times time plus 1/2 at squared. Again, the cart is at rest initially, so that is 0. So delta x, or how far it will have moved, is equal to 1/2 acceleration times time squared. So 1/2 acceleration we just found to be 1.61 meters per second squared, times time. They want to know how far it's moved after 5 seconds squared. So 5 squared times 1.61 times 0.5 tells me the cart will have moved in 5 seconds 20.1 meters. So that's a little more complicated problem because we see that we need the net force, which in this case is the resultant of many different forces. We need net force to solve for acceleration. We needed acceleration, so we could use kinematics to find displacement. So hopefully those helps. Those are some examples. Give the practice problems a try, and if you encounter difficulties, feel free to email me and we can figure out how best to help you.